Okay, all right. Um, any questions? Let me ask from there. Or if you think of any problems that can happen still in this learning. Anyone has any ideas? Yeah.
How to convert in a mathematical model something? Like we are designing things, but if you want to create some mathematical model using this some data you are collecting out of some prediction or something we are generating from data.
Right.
So how do we check this is a problem and this is a solution? Because we are seeing a math, but how to fix it?
Okay. All right. So I'm not sure if I'm understanding your question correctly, but are you? I guess what you're saying is that how do you model a situation or how to create a model? I mean, a model is a model. I mean, a mathematical model. So your question is that how to create a model, right? That's what your question is. Or a mathematical model.
Yeah, mathematical, like you creating something which shows you something. But if I'm creating something, how to generate a mathematical model?
Okay. I mean, so is it a modeling question, that how do you model something? Is that what you're looking for here? All right. I mean, I can talk about for a couple of minutes, but that's not primarily what we are trying to do, because modeling techniques is a discipline in itself. How do you want to model something, right? But I'll give you the basic information that may have already been told by me here. But let me just come back to that in a second. Is there anything else much more closely related to what we were talking about it? Yes, no, maybe? Okay, all right. So let's just talk about that itself. So when you say model something, you got to define what it is that we are talking about, right? Because that's what the modeling is. So there's always going to be a phenomena that you're trying to model. If you're trying to find something, so take an example of something that interests you. So do you have a use case, or do you think something that you want to model? Yes, no, maybe. Do you have something?
Anything you can take, like you are showing something.
Okay, so let me take like two different examples, right? So that most of you can relate with, right? So let's say, think of Tesla. When Tesla started creating autonomous vehicles, right? What do they need to do? They need to model the environment in which their car is going to operate. So that's a modeling problem. So that's one set of modeling problems that we have. The other set of modeling problem could be that, let's say, for example, somebody is trying to study as a financial analyst or as an economist the India's GDP growth and predict something. How do you do that? That's another modeling problem, that you model a phenomena which has some observations or some readings, create a model, and then say that this model predicts, or this model can correctly, accurately predict what's going to happen. And I'm making the assumption here that the model that you're looking for, you're trying to build a predictive model, right? So that's what it is. So basically any modeling depends on two things, is that what is the area or what is the domain that you're trying to model? Do you have observations in that domain? And then what is the goal that you have? What is it that you're trying to predict in a model, right? Now the model could be as simple as I'm saying, in the sense that, let's say, so before I go there actually, so one more thing in a model, every model has two things: dependent variables and independent variables, right? What's a dependent variable? So basically this is an observed phenomena, let's say, whatever, something. Now this observed phenomena, you as a modeler will say that I think this phenomena is dependent on or is driven by, let's say, two variables, V1 and V2. The values in there is X1 and X2. These are actually not called the dependent variable, but these are called the independent variables, because these are the values that you don't control per se. These are the things happening outside. Observed values are, let's say, Y's, Yi. And then you're saying that I want to create a model where I can determine a Y prime I given a range of X1 prime, not prime, these are observed, so X1 to Xn. So you're observing something, you determine certain independent variables that you think impact the value here, and then you try to create a model. That model is nothing but what I've been saying is that figure out a function which, when applied to the independent variable, gives you an estimate of a dependent variable or a observed value. That's what is modeling all about. Now, depending on how well do you understand the natural phenomena that is happening, how well do you understand what affects the natural phenomena that is happening, you can figure out or work a good model. You may also have constraints in the sense that how complex you want the model, how simple you want the model. Okay? So let's take examples that we said. So I said that GDP, that was my one example, right? So those who are doing financial management or economics or something like that, what describes or what influences the GDP? Any idea? Okay, what else? Understand one thing, whatever you're trying to pick as independent variables, you need to make sure that you get some data, right? Now, there's no right or wrong model. You talk to economists, they may have their own model for predicting GDP. So anybody can have it. So let's say I am designing it. So let's say I would say total number of employed people. Let's say I'm going to say that's one of the variable that I want to use in my model. Let's say I want to go by saying, I don't know how many what I can do, but I will go by number of cars sold. Let's say I will go by the amount of wheat produced. You can pick up whatever you want, right? How do you construct the model? You're saying that I'm going to look into the past of this information, year by year, let's say, and then I have the GDP number for that year as well. So one thing I do, which is really the same thing as like learning, I would probably figure out is that given, now I chose these variables, I have the GDP number, I will try to fit a function or a model or a curve which actually can then predict. The same way that we are talking here, I estimate a function, I predict the GDP for a past history, is the GDP correctly being predicted or not, then I modify the number, right? So really all it is an exercise of fitting a curve, right? You may call it regression analysis because that's what it is probably. You may call it logistic regression, multinomial regression, polynomial regression, whatever the case, whatever the function you're trying to fit in. Now, one other thing I'm going to do from this point onward is to take your question and map it to what we are going to talk about next as well. So this is exactly what you're trying to do when you're trying to model a system. Let's take the second example that I had taken, is that the Tesla trying to figure out. Now what they are doing, they're saying that take the data. Now they have gone through and figured out is that what kind of cars, what kind of obstructions, what kind of signs, what kind of lights, what kind of people could be there. So their aim, which is here it was the predicting of GDP, their aim was that can the car move? Should the car continue to move? Should the car de-accelerate? Should the car apply brakes, right? And that is what they're dependent on seeing. The goal is that if I am going by X speed, because there's a lot of different calculation. So they're going by, if the car is moving in the X speed, they require this much of a braking distance before it comes to the stop. So their calculation could be that unless I have this much speed available, I need to either stop or de-accelerate. So their goal is to see, do I have enough space available? How do I do that? Do I need to see, can I see another car in front of me? Can I see a pedestrian? Can I see a car coming from this side, a car coming from this side? So if you think about the picture that I showed, what they're trying to do is that they take an image, which obviously is coming from the sensors, the LiDAR sensors, the movement, or the camera. And if you notice that I showed you a picture, if you see a screen on the Tesla car, because they show the screen, you'll see these bounding boxes. So every obstruction, obstacle, or an object they're trying to identify in a bounding box. If you've done any special programming, special computing or special information systems, these bounding boxes are, there's a person, there's a car, there's a building, there's a pole. They're identifying each of these things. And then the model is calculating, here I am, my car, I need this much of the space available to me unobstructed if I want to continue with my current speed, right? If I have something here, I need to either de-accelerate or apply a brake or whatever the case may be. That model is very, very complex because a lot more things to do, a lot more things need to happen. This is relatively much simpler. If you think about it, the cost of making mistake here are very high, right? Accidents can happen, people can lose their lives also. People have lost their lives here. This is a theoretical calculation, right? I may predict X percentage of GDP growth. Actual growth may be X minus delta X, X plus delta X. It's all a theoretical exercise, right? But yes, I mean, if that's my profession, if that's my job to predict, if that's how I earn my living, then I better want it to be correct model, right? So all that kind of thing. Now, let's connect with what we are going to talk about now. Learning is trying to make sure that you're predicting the correct model here. So let me ask you this. What is the goal of learning? Are you trying to fit a model in the observed data as best as you can, or you want to generalize your model? So you want very specific so that it fits the best, or you want maybe not what fits the best, but what can generalize the response? Sorry? Right, but what is more desirable?
Generalizing would be more salubrious.
Why?
Because if it could chisel it to a particular tailor-made thing, it will only be useful once. However, a general idea can be replicated again and again.
Anybody else who wants to either disagree or add to it?
Apart from the desired outcomes, there are many other factors which are affecting that specific situation.
Like what?
Improve and optimize it also.
Yes, but it is part of the optimization that we are saying. So your answer is correct, but you're not able to give me why. Like explain why. I mean, many of you said generalize, but why? Okay, that's fine. We'll come back to it. That's the part we're going to do in this section actually. This is the question we're going to answer, is that how specific do we want our model, or how generalized the other way we want our model, and why? So think about this way. If you are going to get the best model that is fitting the known data, you guarantee to get the right answer for the known data. But that's not what you're modeling for. You're modeling for unknown situations, right? Go back on the day one. You have knowledge. With that knowledge, you can create a perfect model. But is that intelligence? No, because you need to apply that to unknown situation and then see, does it still give you a decent result? I'm not saying most accurate result, but a decent result. So the goal is not to find the best model for the given data. The goal is to learn enough generalization, or let the model learn enough generalization so that it can actually work with unknown data or unseen data as well, or unseen scenarios as well, or unseen situations as well. Okay? I was trying to locate this morning, but I couldn't find the actual news. I didn't spend enough time, spend like 60 seconds on it. 2 autonomous vehicles collided last week in California. One was Waymo, and I think one was another. Waymo is a car rental agency in California, and not even in California, in several cities in US basically. If you hire a cab, it's a driverless car that will come and will take you wherever you want. 2 such cars collided actually. So one of the I think Waymo had said that their model actually guessed that the other car is not movable. So based on that, their model figured out that there is an object there, but they did not expect that object to move in their direction. So they collided, but then the car said that they collided, but they collided at a very low speed, like 5 kilometers per hour, because as they realized that it's moving, it applied the brake, but still collided. So again, the problem was that their model prediction was that I see the object, that object should not be moving, but the object moved. So the calculation went wrong to some extent. So now that's a modeling mistake, or that's a mistake in the sense that an unknown situation where they predicted that that object, based on its size, look and feel, looks like a stationary object, right? But that was not a stationary object. That also was moving, and then they collided. So anyway, generalization is what our goal should be, that we want our model to generalize the situation. So let me introduce a term called regularization. Why? Has anyone heard this word, regularization? What does it mean? Sorry? Yes, you have a good technical answer, but what does that mean?
To make our models not to learn too much of our particular situations. So
Right.
that,
Why?
Errors and noises should not be learned.
How can you be sure that it's learning error and noises?
Outliers and
Do you know who the outliers are? Can you not exclude them? Okay, you're saying all the right things, but you have gone into like the definition that you have learned. I want you to have intuition of why. So yes, that's what the regularization is. But I was just going in the sense that if you are looking at the Indian newspapers, the regularization is a demand where people say that they were hired temporarily. They want to regularize. You want to regularize them. That's also regularization, right? But that's not what we are looking for. What you said is all correct, but we want to get to the point where we understand why we are doing all that. What's the reason behind it? So the bottom line is the same. So we were talking about how do the models learn. Now we're going to look into how well does a model learn. So you've learned something, but have you learned just like rote learning, that you remembered something, or have you learned to apply it to an unknown situation? So that's what we are looking at. How well does a model learn? And the definition of well is that, can it work with unseen data? Unseen data, now I'm differentiating at one more thing, from an out-of-domain example. Now what is an out-of-domain example? How many of you have seen this term? And I won't be able to tell you because it's a Latin. I mean, especially in statistics, you may have seen this. So generally, when we are proving something, IID, and it's a Latin term. I can't tell you exactly what it is, but basically it says that if the data remains same, or if the data is following the same distribution, that's what we mean by IID when we say. So an out of domain example would be that you are taking a sample from a distribution which is different from the model that we have created, or the model that has been created by the data from a different distribution function. So what we are saying is that how well a model learns is defined or driven by how well it works with unseen data and or an out of domain example. Right? The way to do it is that a good model should be able to generalize, because we haven't yet defined generalize, but basically what it means is that it should not just only learn what it has seen, but it should be able to work with unseen data, out of distribution, or whatever the case may be. Right? Now, there's two other terms introduced here, a robust model or a brittle model. A robust model is the one that is able to generalize more. A brittle model can only work with the data that it has seen, but not beyond it. Think of an analogy. If your learning is the same, that you can answer all the questions if they were taught or they are included in the notes, your learning is brittle. If you can answer questions that were not covered explicitly in the coursework, classwork, homework, examples, then your learning is robust, because you can apply what you learned to a new problem that you have not seen before. So the basic concept is the same, right? So what is our goal? Having a brittle model or a robust model? Robust model, right? So what we are trying to do, how do we train a robust model? So we want the model's learning to be robust. So one thing, the easiest thing to say that, training data as diverse as possible. Rather than solving 5 problems, solve 50 problems. And the likelihood is that whatever the problem shows up in exam, you've already seen it. The same or the exact one. So great strategy. It works in 8th grade, 10th grade. When you get to the problem at, let's say, at the graduate level or at the research level, it's such a vast problem that you can't definitely say that that's the technique I'll do. A lot of students I've seen who are very successful at the high school and intermediate level, because what they're doing is that they're spending a lot of time solving as many problems as they can, finish this book, go on this book, go on this book, without learning the concepts. So it works up until a point, but it doesn't work, because if you're not learning the concepts, somebody can come up with 51st problem, assuming you've solved 50. Somebody else can come at 511th problem, assuming you've solved 510, and you will maybe surprised that, oh, I've not seen this ever. Students will complain, I have done this book, I finished that book, I finished that book, I don't know where the problem came from. It's possible, right? So you want to learn the concept. It's an easy way to say that training data as diverse as possible. Sometimes it's not possible, sometimes it's not even doable, and sometimes it's not even worth doing it. If you are solving the same problem over and over again by changing the values, by changing the parameters a little bit, you're not learning anything new, right? What you could do is that, one other thing you mentioned, the noise factor, right? Pre-process the data so that you are not necessarily bringing irrelevant feature or spurious feature. Some of you who are doing the data science would probably know that data pipeline has a pre-processing step where you're doing all kinds of actions, munging, cleaning, or whatever. We're not going into the detail. Bottom line, if you know the domain from which the data is coming, you could do this. Otherwise, a bigger problem there is that how do you know which one is irrelevant feature? Because you don't know at the beginning. If you know that, you can avoid it, right? Spurious feature. Now, one other thing I'll say that actually, something I mentioned yesterday, principal component analysis or dimensionality reduction, is an exercise in these things, that irrelevant feature. So if, let's say, you're trying to build a model and you have 80 different features, that too many. Anybody in data modeler will tell you that if you're trying to build a data model with 80 different models manually on your own, it's too much. Fine, large language models are building it with so many features, but that's a totally different ball game. There what you do is that you try to find out of the 80 features, which features are more meaningful. That's principal component analysis. That out of 80, maybe you can figure out 15. So there are multiple ways. Some you can say that this feature is dependent on this feature, so I can ignore this. You can actually figure out the dependency, this feature is dependent on these 3 features, so I can ignore this because I already have these 3. All of those are irrelevant or spurious features. Irrelevant features who do not bring information about the label value. Spurious features which are already correlated with some other feature in the data. One of the examples which they have used in US at least is trying to predict the value of your house. And then they say that what is the relevant value? Number of bedrooms, number of bathrooms, number of floors, area of the size, location, how far it is from Starbucks or whatever the case may be. Different people have come up with different models as usual, but you want to avoid irrelevant features and spurious features, right? Generally, you're trying to make assumptions about the data. So better you know the domain, better you would be able to model it. So that's what we are trying to do. I have still not defined the regularization, so I'll come to that in a bit. But what our goal is now, goal is shifted from learning or training to training a robust model. We just don't want any model, we want a robust model. So how do we do it? 3 of these things I mentioned here, let's just continue to do that. Now, depending on how many training examples do you have, if you have smaller number of examples, then you're making a very strong assumption because each of these examples will contribute a lot. If you have a large set of training examples, you do not want to make any assumptions. If you extend this thing to a large language model, you're making no assumptions. You're making let the model discover every relationship, every feature on its own, right? Generally, what you do when you have the training data, you do not use all the training data. You basically use 80%, 70%. You leave the 20, 30% data to validate your learning, right? And it's really important, again, knowing the domain is that how do you divide the data? Sometimes the learning that you do is that you take the different batches and sometimes intermix the training data and validation data and then use overlap data to figure out. All of that work you're doing is that so that you're generalizing the model that it's learning. Okay. I'm not going into too much detail, but basically what we are saying here is that let's say you had 100 data points, you use 80 to train, you use 20 to validate. They're coming from the same known data, but then if it works with those 20, great. Is that the best thing? Or does that guarantee that your model is generalized enough? Yes, no, maybe? Okay. So before we go into this, what can go wrong? Or what is it that would not let it be generalized? That's an unseen instance, right? Yeah. Any idea? How many of you been to India Gate in Delhi? Couple of you. So, first time I went to India Gate when I was 12 years old. It was very different days, obviously. You could take your car, and actually it was a political rally, so you take a bus, and then the bus was parked there itself. And then you go out, and then you say, okay, where did we park our car? We say, okay, let's use the India Gate as an example, right? So what are we doing there? We are creating a model to find out the path back to where we had parked, right? Is it a good model or a bad model? Any idea? I can give you multiple examples of personal examples where we made a mental model of where we have done something and then had issues with it. I'll give you two more examples. But why is it a bad idea?
It's actually a good idea, sir, since that landmark is quite prominent.
Okay. You think it's a good idea? I can tell you it was not a great idea. It took us a while to find where we parked. Can someone tell me why is it not such a good idea? It is not a bad idea because you're taking a prominent landmark and that's what you're saying, that let's find a landmark and then we'll come to the landmark.
There might be many other vehicles also parked, so you have to find out.
There's another problem with, and that's the reason why I took the India Gate as an example.
Must be aware of the direction because India Gate.
Correct. Because when we have fixed the India Gate, but the problem there was that a lot of open space, all 360 degree. So just one thing was not enough. It required a vector. It required a direction also. See, southwest of India Gate. So the relative position was not obvious. So now you have to kind of circle around to find where exactly, because every place was same, right? So let me give you another example, and then I'll tell you why I'm giving you this example, unless someone tell me why I'm giving this example. There's a town called Charleston in a state called South Carolina in US. We went to Charleston. We parked the car. We parked the car in a church. And we said, okay, that's a great model because we have parked in the church parking and then we'll get it, right? Sure enough, 2 hours later, we couldn't find where we parked. You ask a local person, it's in a church parking lot. The guy says there are 200 churches in Charleston. So what mistake did we make? Thought there might be 1 or 2 churches and it will be a good enough benchmark or good enough landmark to go and find. He says there are 200 churches. Which church? Oh, we didn't really think of getting the name. So what is happening here? We are learning, but what are we doing here? Can someone tell me the mistake that we are making? Sorry? Yeah, but which one is a bad assumption? Like, what is going on here? So first of all, we are doing discriminative learning. We learned a feature. In the first example, India Gate was a feature, but we gave too much of weightage to that feature. Similarly, we said we are parking in a church. Church is a good enough feature to locate, and we gave too much weightage to the feature. It did not generalize because when we got the data that there are 200 churches, now we had no way to distinguish which of that church, right? So it happened. We asked first person, he sent us to the nearest church. Our car is not there. Then we ask another guy, he says, okay, there's another church there. Now we're discovering the unseen data and it is not coming out to be the right one. So what mistake are we making here? I said so, but tell me.
Poor weighting.
Right. So actually, I would say that we are weighting certain features very highly and hoping that that is a discriminative enough feature to determine is this the right answer or not. Okay? So that's one way of doing it. I'll come back to that. The other problem is the overfit. When you do not know, let's say we were trying to locate based on every such building that, okay, not only it's in church, it's next to a 3-story building, which is a red color building. Okay, we're trying to generalize, we're trying to introduce a lot of specificity. It may be a noise, we're trying to overfit as much as we can. Oh, there was a McDonald's out there, there was a 3-story building, it was a yellow colored building, there were 3 more cars parked there. A lot of it may not be even relevant. We are unnecessarily complicating the data and may not be able to generalize. We come to the same spot, instead of 3 now there are only 2 cars, but our model says that there has to be 3 cars. So you move on, even though that was the right space. So you do not want to overfit the data as well. Okay? A good model should be able to generalize. Now, what is regularization? That what we are trying to define is that controlling the capacity of a model. Now, capacity of a model is in the sense that It should be able to generalize to not have the overfit of the data. And the other example I gave, do not have features which are overweighted. Does that make sense? So the regularization is a process by which you could say that I do not want overweighted feature in my model. So let's say I have 10 features. I do not want a single feature which has a weightage more than 15%. The first example, when we took India Gate, we said that is one feature, 100% weightage. It was a mistake. Church, we said that enough, 75% weightage. If we get to the church, we'll find our car in the parking. It was a wrong assumption. So what we are saying is here, regularization is a process by which it says that if I discover that I have features which have larger weights, I want to avoid that. Either I'll drop that feature, I will reduce the weight or something, because I know if I have features which have larger weights, the model is not generalized enough because it's giving too much weightage to one or two features, and it's going to be always skewed in favor of that, right or wrong. So regularization is the process. Now this example you had seen before in a different context, that's the observed data. The best fit curve is this. Is it the best generalization? No, maybe best generalization is this. How do you avoid that in a mathematical terms? We are going to say that we will go through a process called regularization, and I will define the regularization and the kind of regularizations that we are doing. So in a way, the question when you start ask about modeling is related. We started with learning. Now we are saying that when we create a model, when we are learning, we do not want features which have the larger weights. So if you build a model too powerful, it can overfit the data. What's the problem with overfit? Because it may not work with the unseen data. So you do not want a powerful model. You want a relatively weaker model that can generalize. So what your goals are: avoid overfitting, regularize, which means that do not have features which have higher weights, and in the case of neural network, actually drop out. Dropout means that don't use all the neurons that are available to you. Now this also is based on discovery as part of the research. Same thing, don't overemphasize on one thing or a few things. In this case, the way the dropout works also tells us is that increasing the size of the network is not always the best option available to you. So what we would see that in the case of the learning and neural networks, sometime the best approach is to drop some output of some neurons. Use the less number of neurons. So I'm going to go spend some time on the regularization. Again, I'll skip out the maths portion of it, just get the intuition. But those of you who you want, you can think about it, what you want to do. So what we are doing here is that this was our loss function. What we are doing is that we are adding a term which we call as a regularization term. So what we are saying is that rather than calculating the true loss function that we started with, we are going to change the loss function in some way, shape or form that will help us generalize the model. How are we going to do? We're going to penalize the large weights, because that's what we learned. If you have a feature that overly dominates the output of your model, it's not general enough. So what we are going to do, or what the regularization is, that it changes the your loss function by introducing a new term. What that term does is basically says that if there are large weights, reduce the impact of those. How do you reduce the impact of those? By reducing the loss function value by something. See, if you think about it, if you're saying that a factor has an oversized weight, then it says that, okay, I see the India Gate, that means this is the place. It says no, reduce the loss function in the sense that it may not be as much right as you think as it is right. So that's what we have done. We have introduced a function. Now there are multiple ways to define these regularization functions, or like what they should be. One of you asked, what's the scientific reason? No, the science is being invented here. We notice that if we are doing a discriminative classification, 2 hours ago I said that you find out the most dominant feature and then you say that if this feature exists, you can classify. Now I'm saying that if you do it too much, that's also not good. Why you don't want to do it too much, how you want to avoid it, we are saying that we want to calculate, we want to reduce the loss function so that we would say it's not really the right thing, because we are taking the opposite of the loss function to modify the weights and biases. If you have a large value, you will modify by larger number. So you reduce the loss function, so you will modify it by a little bit. So that's what we're going to do. Now, what that function should look like, we're discovering. It applies, it varies from problem to problem, domain to domain. I'm going to look at 2 or 3 different type of regularization. One of that being dropout, where if it's a neural network that you're training, you avoid the output of certain neurons. That's a totally different research problem, which neurons, how many neurons, etc., etc. But again, that's one way of doing. So easiest way is called L1 regularization. The way the L1, now L1 also comes from linear algebra, from matrix multiplication, matrix manipulation. Norm of a matrix is called the, is used for L1 regularization. Sum of the absolute values of the weights. So if that is high, we're going to take that number and reduce it, reduce the loss function by that number. Now this is the absolute value, so they're not cancelling out. So one way that we are saying that if the weights have already become very high, let's reduce the loss functions, which means that the weights will start getting smaller. Why? This was the most obvious thing. We said that we do not want overweight features. So if the weights have gone higher, reduce them. Does it work? Yes, it does work. Now, can I explain to you why is it working? Not yet. But intuition is that because we do not want bigger or larger weights, we are reducing them if they go beyond a certain value, right? So L1 regularization is very simple. Whatever is the cost function or the loss function, you basically calculate the average weight, sum it over, reduce it by number of 9, multiply it by the learning rate, eta, we saw this earlier, and then basically you are trying to penalize the large weights and hoping to build simpler model. There are advantages. Relatively simple model, it avoids the peculiarity of the noise in the training data, hopefully learn the real learning and generalize better than what it learns. Make sense? Yes.
So we are finding it a bit challenging to retain all this information. Like, will there be any hands-on segment within this course?
Mean trying to do some exercise?
Yes.
Unfortunately, no, because what I was told is that there is like a varied thing. If I ask you to write Python program, half the people probably don't even know how to write the Python program. So I'm going to share this stuff. So I appreciate what you are saying here, right? But think of it this way, and this is where you need to be learning in the sense that retain what you are learning here and apply in different situations. I agree with you, but I'll give you all these notes. I'll give you all the pointers that you want to do. One thing that I hope you gather is that majority of the thing that you are learning here are very similar to things that you have already seen somewhere, or I am trying to connect with multiple areas so that you retain some of that information. But yes, there is no substitute for doing it on your own, which is why I asked this morning how many of you did that learning exercise for AND, OR, and exclusive OR gates, because that's the simplest learning exercise you can do. Simulate the learning. So do that, but no, other than the case study I gave, there will be another case study, a single case study for everyone, but that will focus more on the social, legal, and regulatory issues specific to Indian situation. Talk about that maybe Tuesday, Wednesday next week, so we'll see how you deal with it. Do you guys follow the case study method of learning here? especially in the management and anywhere? Yes, no? Okay, all right, fine. I haven't seen the cases that you're doing here, but let's see. I'll share one with you guys. How large are your cases? 2 pages, 20 pages, 50 pages? 1 to 2 pages? Okay, fine. I'll make sure that I don't give you too much information then. Okay, all right. So that's one way of regularization. It's called L1 regularization, right? Does anyone see an issue with that or a problem with that?
What is criteria for choosing a learning rate?
Sorry?
Learning rate. What is criteria for choosing learning
The criteria for choosing the learning rate?
Yes.
Can anyone answer that? We were talking about it earlier today, just before we took the break. Come on. Anyone? The learning rate was the step that you were looking at it. You do not want too much of a learning because you may skip the actual minima, or if you go too slow, it might take many iterations for learning. So there is a trade-off. You want the right one. I mean, it comes from the practice or experimentation. So the learning rate is basically, so if you go by the basic principle or first principles, what is learning? Learning is weights and biases. You start with a random weights and biases or an initial value. There was also a research that should you start with zeros and ones or give the random. What was discovered that you should start with random because it doesn't matter where you start, it should end up. So the learning rate is that how fast do you want to change the weights and biases to get to the optimal value. We saw the example, and I gave you the example of Newton-Raphson finding zeros. If you are learning too fast, moving too fast, you may skip the minima and you may kind of oscillate here and there. So if someone remember Newton-Raphson, as you try to get closer to the minima, you are reducing the size of the step by which you make a move. You can do that here itself as well. Actually, I think I have a slide here which gives you suggestions if you are trying to implement learning. So I'll come to that. Learning rate is also a answer there, but that's where the learning rate is. Okay, let's come back to regularization. So do you see an issue with the L1 regularization or the way I have defined it here? When we are trying to fit a curve here, do we follow the Manhattan distance or the L1 regularization, or we follow something different? I used the term last week, mean square error, right? So the way we do it is that we square the difference and then take a square root of that, right? Here, all we are doing is that taking the absolute value, so we don't end up, but what is going on here is that it's always penalizing in one direction, right? I mean, which is perfectly fine, but all weights are equally accounted for because you're just taking an absolute number and adding it up. So the contribution of a smaller weight is in proportion to its size with the larger weight also. You get my point? So if let's say you have two weights, one is 3, one is 10, in the L1 regularization, let's say it's -3 and it's 10, right? So we are doing the mod of it, and we are saying that the regularization term is 13. So 3 and 10 both are contributing in the same way. Was that the goal that we started with? Does anyone remember what the goal was? Why did we introduce the regularization function? What was the goal? Sorry? Yes, but how are we solving the overfitting problem? Correct. Penalizing the large weights. Are we penalizing the large weight here? right? So we need some way that the larger the weight, it should have a larger contribution towards reducing the cost function. How do we do that? So the second possibility, what is called as L2 regularization, says that rather than taking the mod, you take the sum of weight square. So instead of 13, this becomes 9, this becomes 100. Now this has a larger weight. Does that make sense? So the L2 regularization is also called ridge regression. It takes the sum of the squares of the weights. Right? Now again, there's no scientific reason. I mean, there's an intuition that we wanted to penalize the larger weight. So you take the square that will make sure that the larger weight contributes larger, reduces the objective function or loss function much more than a simple one. Make sense? All right, this is again the same definition that you've seen before. The cross entropy function, and you add the L2 regularization to that. I'm not going to go into the detail, but this is the basic intuition. What exactly is going on here in these two examples? The learning in the network is going to prefer the smaller weights more than the larger weight. If you happen to be with a neuron where a certain input feature has higher weight, just like India Gate given a higher weight or a church given a higher weight, it will tend to discourage it, right? So that's what is the regularization function is doing. So why do we need regularization? We need regularization term to avoid overfitting, which means not necessarily unduly give weightage to one or more features. We do it by introducing a term called regularization term. We looked at two examples of regularization term if we are following this. One is called L1 or a lasso regularization, which is simply letting the sum total of each weight get subtracted from the loss function. Then we realize that each weight is contributing equally, whatever in relation to its size, but we wanted to make sure that the larger weights are penalized more. So we kind of, rather than adding the absolute value together, we are squaring them and adding them up. All right, so let's see. What are we saying here? I think I've covered almost everything on this slide. So have a quick look at it and let me know if you have a question. Yeah, regularization, I've done everything else. All right, so the last method of regularization that we're going to talk about is dropout. Now, I'm only giving the intuition here, not even the formula here, because there's really no formula. What the dropout regularization does is, in the case of deep neural network, it chooses to drop out certain neurons to contribute while it's calculating the weights and biases. Now, which neuron, how many, how much is an entire different mathematical ball game. From intuitive perspective, understand one thing, that after L1, L2 regularization, which is again modifying the weights and biases, it has been, by the researchers, empirically observed that if a neuron is contributing too much to the next layer, sometimes dropping that makes the network learn better. So that's another way that the problem of overfitting or not being able to generalize has been resolved. Okay? All right. Any question or questions? Yes, no, maybe? Okay. It's already jumped to the next slide. But let's go back. Any questions?
So in dropout, we are ignoring the data itself.
We're ignoring the output of certain neurons. So if you think about it, in the neuron, on a neural network, you take the output of a neuron, it becomes input to the next one. So you're zeroing out that neuron. And the intent there is that by doing that, the network is learning better to generalize. Right? I mean, the basic intuition is same. If you let one feature to dominate your discrimination capacity, generally you'll end up making a mistake. Think of it, apply this in your own mind, that did you make an assumption about certain feature to be present all the time, right? And then I'm trying to remember a Hindi movie where, if I'm not wrong, it was Amitabh Bachchan's character was he blind or he plays blind, and then he actually picked out features. And the scene that I remember is that he had remember a turn where there were the church bells or some bells, and then those bells are not there, and then he gets confused. Doesn't even remember, and maybe a 20-year-old movie. Fine, forget it. The bottom line I'm saying is that anytime you're trying to model something, avoid giving too much weightage to one feature, because it might work, but it may not generalize all the time. So that's the whole intuition behind regularization. That's all we're trying to do here. All right. Any other question? Okay. If not, we're going to go to the back propagation. Now, we have looked at back propagation a couple of times, right? I'm going to just give a slightly different viewpoint, again from the perspective of how to generalize the model, how to improve the performance of the model on unseen data. So part of it would be recap of it. The focus today is to come up with an algorithm. So you see what the algorithm looks like, but majority of it should be same. We know the back propagation. It's really calculating the partial derivative, which is really the cost function or the loss function with respect to every weight, and then you use that to propagate it back to update the weight. What we learned today is that we want to introduce a regularization function so that the weights are not directly dependent on what the cost function is, because if it's giving a higher weightage to one neuron, one feature, we don't want to do that, because that is not necessarily helping us. So you've seen this earlier before, that this is the W324. It's really the kth neuron in the L-1th layer to the jth neuron in the ith layer, in the sense that what weight is being driven by. So it will use this. This is just a notification here. It's important if you are programming it, because when you do the metrics calculation, that you will figure out here. Now, the way we do it, we don't want the metrics multiplications because those are very expensive. We use, and I referred this, the Hadamard product, or the linear multiplication of two metrics, or element-wise product of two matrices. That's what we use to calculate avoiding the regular matrix multiplication. So we use this method, and I'll just give the backpropagation algorithm that is being used by the deep neural networks. So it's a less commonly used one. S and T are two vectors of the same size. This is the multiplications that we use. So if you think about it, if you're trying to multiply 1 to 2, a vector of 1 and 2, two values, with 3 and 4, if you're doing the common matrix multiplications, you can't even multiply these two matrices, right? Because you need one row and one column to multiply this. The result here would be a same size matrix. You do the element-wise multiplications, 1 multiplied by 3, 2 multiplied by 4, and this is what you get the result. So this is the product that we do to calculate the weights and biases. Now, again, somebody might ask that, what's the scientific reason? Then, why are we doing it? Intuition, because it's a much faster multiplication. It reduces the requirement of matching the number of rows by the number of columns. You can multiply by vector by matrix, matrix by matrix, or vector by vector, whatever the case may be, it will work. It's element-wise multiplication. It's faster, it works, that's why it's used. hopefully somebody will come up with some theory, theorems, prove them, lemmas, whatever. We are not there yet. We're just discovering right now. So the algorithm looks like this. Now we have talked about it in multiple different ways. I'm not going to go too much in detail. Just explicitly writing out in the form of an algorithm, but we have figured it out. We have done it all. Input, feed forward process, output error calculation, back propagation of the error, and then the gradient is given by the partial derivative functions that we have. If you look at actual step of this code, you might find lot of code out there, a back propagation algorithm, probably a couple of hundred lines of code that can implement this. So those of you who either have interest in developing or writing code, look around. I can give you some references as well if you want to write your own learning algorithm or neural network training algorithm or implementing the back propagation specifically for it. That's what you need to do. Okay. I think the next few slides would also be the similar thing. We have seen it all. So I am not necessarily spending too much time on it, but let's just make sure it will answer the question, the learning rate you said. So learning is finding right weights and biases. Learning rate, the speed with which you change the weights and biases to find the right one. One key thing actually on this slide that tells us here, and this is also one of the reasons why learning rate is important. As a human, we learn best when we make the mistake, the most egregious mistake. That's when our learning is best. Not so in neural network. We saw this in a slightly different way yesterday. If the neural network makes one mistake, it can't recover from it. It will keep on making more mistakes. As a human being, when we make a mistake, that's when we learn most. When you say, okay, I'm not going to do this, right? Like I made one mistake that time that used the India Gate as a landmark for parking or church as a landmark for parking. I'm not making the same mistake again. I'm using as an example here. So humans learn best when they make the most egregious mistake. The neural networks go the other way. If they have made a mistake, they can't recover from it. They learn slower when they have made a mistake. Humans learn faster when they make a mistake. So there's one difference here. That's what it is. Artificial neuron has a lot of difficulty learning when it's wrong. So that's a problem that you have to figure out. Far more difficulty when it is just a... So more wrong it is, higher the problem that it will ever recover because it's not learning. So if you think it in a slightly different way, the neural network is always learning in one direction. So if it has gone bad in one direction, it's not easy for it to recover. That's where we are doing the regularization to some extent, not let it make larger mistakes either. So that's one thing that you are learning on this slide. You've seen this formula. I'm not just necessarily going in any more detail in this here, but another way or intuition to understand the cross entropy is the last line here, that it's a measure of surprise. In the sense that, as I said, that the neural networks are not exceptionally good in learning from a bad situation. The cross entropy function gives us some kind of a measure. If it's going high, we know that the network is not learning better or good or a good speed. So we are trying to learn fast from their error. One of the way we do that is, how do you give the initial weights and biases? Now I mentioned that in passing that you randomly assign it. Some researchers have shown, was it here? Yeah. Some researchers have shown that in some domain, it's not yet established research, there may be a way to assign initial weights which can do one of the multiple things. Either learning is fast, learning is more generalized, bad learning is stopped. So there is a possibility of doing it. No established research, but weight initialization is an active topic of research specific to a domain, specific to a problem, right? How to choose hyperparameter. It's also an art right now. People are good. It requires massive effort. Why? Because as I mentioned, learning is slow unless you have a lot of resources at your hand. Even at that time, each run is costly. So you do want people who choose the right hyperparameters and a good hyperparameters. In general, what we have understood, if you want to do non-trivial learning, reduce the training sample size. What we are saying here, so it's slightly counterintuitive. 2 days ago, I said that large language models are effective because they are large, because they are learning larger training data. Now I am saying reduce the training sample size, because not necessarily the larger sample size is having the right amount of learning. As a matter of fact, one term that I have not introduced, which we will not introduce, called mini batch learning. I don't know if any of you have come across this term. Rather than having one large set of learning, you want to break it down in mini batches and then run the multiple cycles of those batches. That's what has been observed as doing a much better non-trivial learning. Now, all of this is based on, so the same way, if you want to figure out is that what's better, one annual exam, right? So that's same as mini batch learning if you think about it. So there are a lot of things that people are applying and seeing that it's working. There's no theory, scientific theory at this point of time. But mini batch learning would be very akin to periodic quizzes to confirm that your learning is right or your learning is correct and things like that. So that's what mini batch learning is doing. Less categories, which basically says that don't try to have a softmax which has thousands of categories. So this is again a very counterintuitive finding. Even though you want your network to be able to distinguish between tens of thousands of features, hundreds of thousands of features, but you do not want at the time of learning you have a softmax layer which has so many outputs. That doesn't necessarily help, it only increases the cost. Okay, so continuing to talk about the hyperparameters. General suggestion, now this is just a suggestion here. Start with no regularization. So lambda is the regularization constant, starts 0. You determine the learning rate, which is eta. And then within that, you need to figure out the using a validation data to good starting point for regularization parameter. You can start with 1, which means that when exactly you are adding the regularization and then add or decrease it by a factor of 10, which means factor of 10. So from 1 you go to 10, from 10 you go to 100, and similarly when you're coming down by a factor of 10. Once you have figured out the magnitude, then you can fine tune the lambda or the regularization. Once you have established with the regularization function at least the magnitude of the regularization function, you can start optimizing the eta again, which is the learning rate. Yeah, using the choice of eta, figure out one. So there's a lot of iteration between these two things, the learning rate and the penalty that you want to impose on the feature with a higher weightage. So both these two things. Okay. Even after doing all this, do you think the predictions are perfect? Things can still go wrong. So why predictions are not perfect? There are multiple reasons, right? What can still go wrong? I mean, I have it here. There's an inherent uncertainty in the sense that unseen data, there's a lot of uncertainty. If you have not seen it, you've not seen it, right? Data shift. Data shift is same as I was saying is IID, in the sense that your understanding of the phenomena was that it follows whatever, normal distribution, Bernoulli distribution, but then you didn't realize. So let me give an example here. The best example is in the sense that the things happen in the burst. Let's say you're modeling cafeteria, right? Now you have modeled the cafeteria, let's say for 1 week. Unfortunately, all the time it was when the classes were on, you got certain data. You create a model based on that. And then when you start implementing the first break between the classes, and suddenly you say that, whoa, I never seen this much crowd in the cafeteria. So the data shifted because you never sampled when there was a gap between the two classes. So the demand can come in burst. So that's what the data shift basically, that too much data and then in production data is different. When you learn, it was a different data. When you're using it, it's a different data. Lack of example, you may be missing the data. So if you think about it, a lot of counterintuitive things. On the one hand, I'm saying is that use the mini batch, but I'm also saying lack of examples. So you're trying to avoid a lot of same data, but you do want a lot of different type of data, a lot of different examples, edge cases, right? So a lot of it is art. When you're training, and it's somewhat of an art. But having said that, I said large language models actually are going at the kill in the sense that they want to consume all the data that is out there. Is it helping? Not helping. Somebody asked yesterday, and I had mentioned it earlier also, because they're running out of data. And what has been experimented is that if they consume their own output, the quality is getting down. Right? The quality is getting down. Now, one other thing that I can give you an example, it's like a little bit of a tongue-in-cheek example in the sense that one thing the American universities do is that they would usually prefer undergrad from another university as a grad student in their university. Not exchange, it's something else that I'm talking about. Similarly, if you have taken a PhD from one university, they wouldn't hire you in the same university. They want to hire from a different university. Because if you're not generating new ideas, which is the same thing here, your quality of the output is going to go down. So you want the cross-pollination of the ideas to bring people from different areas. This happens all the time, and I can give you from my own personal examples. The same thing happens in the case of, it may not be true, it may not be possible in this country, but if you think about it, a lot of medical diagnosis is also based on some kind of a modeling. So many of you may have come across the term as the second opinion, right? So one thing that they say, at least in the United States, and you can find out there, is that if you're taking a second opinion, go to a doctor which went to a different medical college. Because if the two doctors have gone to the same medical college, they have learned the same thing, same way, they're going to have the same opinion. It's not going to be a second opinion, it's going to be the first opinion second time. Right? Same thing here. So we are saying is that you do not want too much data, like same data repeated 10 times, but you want 10 different examples of the data. Right? So again, these are all anecdotal examples or the intuitions as to why we do certain things or why we work certain things certain way or they not, right? Okay. Any questions? Let's talk something different then. Should Virat Kohli retire? They didn't do very well today as well, right? Okay. All right. Any other question?
In the United States, which state have you been living?
Which state do I live in? New Jersey for a long time now, 25 years. But was in California before that. But now in New Jersey.
Sir, have you ever ridden a driverless car?
Have I? No. But my son has been. He has. He has taken the videos also.
Intervention in the ride?
No, there's no driver. Zero.
No driver, but intervention of the ride.
No, you're sitting in the back seat as a passenger. I can show the video. I probably have it on my phone somewhere if you want to see how does it feel like. But it's happening. It's happening in many places. All right. Any other question? We still have a few more minutes actually. I have few more things to go over, but that's fine. And if you want to ask any other different question, that's perfectly fine. I'm okay with that.
Sir, can we introduce inside neural network as a fuzzy number?
What do you mean by that? So it's a good question if you want to think about it. Now, what is a fuzzy number or what is a fuzzy logic? Let's put it this way. The fuzzy logic is simply saying that the end of a two numbers, 0 and 1, is not always 0, but it's somewhere in the middle, right? So if you think about it, the fuzziness in our understanding so far comes from when you are replacing a sigmoid function, which gives you a definitive answer of 0 and 1, by a softmax, which gives you probability of one of many answers. So from that perspective, the fuzziness as neural network is more from probabilistic perspective rather than a true fuzzy logic perspective.
So when data is noisy,
Mm-hmm.
in that case, can we implement it here as a rule base, as a Mamdani rule base?
As what?
Mamdani rule base.
What is Mamdani rule base? I don't know. What is that?
Suppose, like in cases, if some in patient's perspective, the patient has a shopping long time, fever, high fever, cold cough, then what is the situation of health? This type of
So, I mean, if you think about it, I mean, I mentioned this, I think, on the day one. For a long time, the artificial intelligence community thought that the expert systems is the way to go, which means that they thought that the knowledge is always like rules driven, and all it matters is that if we can codify the rules, we should be able to get to the right answer, right? I mean, a lot of some of you, if you're doing a data science, you would know that decision trees are being used, right? And you try to create the decision tree by identifying the feature, give higher weightage to the feature that has the most discriminatory power, use that at the topmost level, and then you start going down. All of these things are establishing rules. And if you think about it, the learning is doing the same thing. The only difference that is happening is that an expert is not defining the rules. You're letting the network learn itself what it thinks is the rule. So it is a rule-based system. The difference being that the rules are not prescribed by an expert. That model worked. That model worked for chess, for example, right? Because the chess is a very well-defined space. The board is defined, the moves are defined, and the win position is defined. All that was needed is to codify it and have a computer powerful enough to go ahead of a human being, right? If you think about it, what's the difference between one chess player versus the other chess player? Two differences. One, that player has seen more move if he's an experienced player, and two, he can manually calculate the second move after the first one, third, fourth, fifth. I gave an example that Garry Kasparov, who was a world champion, theoretically, it was said that he, at every move, he was thinking 20 next moves that you might can make. So all they needed is a computer that can think 21 or more, and eventually they defeated him. So some domains you can have rules or a rule-based system, others you can't, right? Now the question of fuzziness, so let me just go back 10, 15 years now. One of the things that when I was working in financial industry, specifically part of the risk management, you deal with a lot of uncertainties, right? Now, how do you deal with those uncertainties? You assign mathematical numbers to them. Like we talked about risk yesterday. What is risk? Risk is nothing but a number. Yeah, and the number is calculated based on the likelihood of bad outcome and the cost of that bad outcome or loss due to that bad outcome. Multiply the two numbers, you get a risk number. Same way, if you have uncertainty about a number, you make an estimate, but associate with that estimate. One of the way that we used to do is a distribution, which is the same as probability or probabilistic inference. So if you think about it, and this is true about when we were trying to get the GDP in. So let's say this is the number we want to know the value of. If we know this number for sure, or the value at this point for sure, let's say here, we're saying that there is no uncertainty involved. which means that the distribution here is a point distribution. There is no uncertainty. Then we say that, okay, if we do not know this number for sure, then what we are saying is that this number is not just this. Let's say it's following this distribution. This number can be anywhere here. Right? That's what we are saying. Now, the moment you have defined a function around which this number can be sampled from, that function can be represented by, that's what I introduced the term moments yesterday. If let's say you are modeling the uncertainty around not knowing the exact value of this point, you're saying that I am saying uncertainty can be modeled using a normal distribution. Now, how do you tell normal distribution mathematically? And somebody asked the modeling questions, the same thing. Every normal distribution is defined by its moments. What were the moments? Mean, standard deviation. There are 5 moments actually that we talk about it, right? Mean, standard deviation, skew, kurtosis, and I'm forgetting the 5th one. If somebody can say it out. We want to simplify more. Then we said, let's make it standard normal distribution. So you standardize the normal distribution, which means that mean is 0, standard deviation is 1. If you can do that, then you only have 2 numbers to deal with. So what we are doing here is that we are converting the fuzziness or not knowing the exact number into some kind of a probability distribution, and that probability distribution tells you, or whatever inference you want to draw will be a probabilistic inference, which is what the softmax layer is doing for you. So same things, just being done differently, right? All right, any other question? Okay, few more slides. You've seen most of them. We'll just go by. Replacing, what we talked about was the binomial logistic regression, and we introduced the regularization term there. I'm not going into the details here, just giving you an intuition. What would you do if you have a multinomial logistics regression, which is really that probabilistic inferences because you're using the softmax layer, right? Generally, we have more than 2 classes. Even if it's the sentiment analysis, it may not be just positive or negative, it may be positive, negative, or neutral, for example. Part of speeches, you might be figuring out noun, verb, adjective, adverb, preposition. So you would see many times that the binary logistic regression may not be the right way to do it. In general, in life, there are more than 2 choices, right? So we use the multinomial logistic regressions, which is a softmax regression. It's giving you probabilistic inferences, right? We've talked about all of this. You are taking a softmax function, which gives you a probability distribution. Each value will be in a range from 0 to 1. They will all add up to 1, just like probability, right? This is what the softmax function does. You've seen this all before, so I'm not going in the detail. That's exactly what you're doing here. No changes for regularization perspective, because regularization work exactly same way as we have done here. Okay, so again, I just wanted to give you a little bit of an intuition. Let's just summarize in the next few slides. What have we learned actually the entire week, right? So I would say that read through it, and then if you haven't understood something, let me know. There are 2 new words here, but my assumption is that you would probably know these, parametric and non-parametric, right? So I think, or I hope you should have learned a couple of bullet points here, 6 here, and I think 6 in the next slide as well. If you have not learned at least these very high-level points, let me know. Right? Model, somebody asked the question, the model. The model is described by either a formula, a program, or a neural network. That's what we have seen. When I say formula, I mean either a linear regression or a polynomial regression, whatever the case may be. Non-parametric, those are parametric model. Parametric model minimize a cost function on a training set. We talked about it for last 2 days. Non-parametric models make prediction by comparing the new example with the training example, which is really the discriminating by a feature. Goal of machine learning is to generalize to unseen data. Capacity can be tuned to improve performance all along, right? That we learned is hyperparameters need to set before the training begins. We saw the hyperparameters include regularization ones, the training rate, mini batch size. We didn't go into the mini batch, but I'm telling you that's another one. Generally, the good parameters will be obtained through a validation procedure. The validation procedure means that don't use all available data for training. You take some, leave some for validation. Make sure that you use the training data to learn, validation data to tune the hyperparameter. Some methods work better than the others. We always know this, that depending on the domain, I always mention that depending on the domain, you got to figure out. If you have better features or more training examples, it will improve the quality of a model, not always. So better is important. Just the more training, if you have the same, like I gave you example of second opinion, which is if it's the same opinion second time, it doesn't really add any value, right? Easy to get. If you're training the model, you always feel happy that you have come up with a very good model till you realize that it's not necessarily a good one. You should put effort in creating a good testing sets as well. You all agree with that we covered most of these things, if not all? All right. Any question? Yes, no, maybe? Okay, we can stop here. Maybe you want to let Professor Sahu know if you want to do something. So when we come back next week, right, there are two things that we have not covered about the neural networks, right? One is the transformer, one is attention. Doesn't matter whether you are from the management or computer science or data science or any other field, right? If you're telling someone that we did a course on large language model and cannot explain what a transformer or attention is, they won't believe you. So I'm going to talk about transformer and attention next week when we meet. I'll try to skip the mathematics as much as I can, but I do want you to have intuition of what these things mean. So we'll go into attention, right? Intuitively, you all know, I guess, right? If you're paying attention in the class, you learn. If you don't pay attention, you don't learn. Same thing applies here. As a matter of fact, what we will do is that we'll see that how do we make sure that the network is paying attention at the right time and at the right point. Okay? All right, we can stop here. If you guys have a question, I had 4 or 5 more slides, but I'll stop that. Let's just ask if you have any questions. How many of you, or if any of you, has work experience? Yes, no, maybe? You have work experience. In between your undergrad and grad, or research, or what? Or you did an internship? You're working right now. Okay. So without telling any secrets, what is the project you're working on?
I'm on the project of anti-northern project, alternative.
Okay. So all of it was noise. Tell me what the project you're doing. I mean, you gave me information, I didn't learn anything new. So what project you're working on?
I'm working on, like, whenever someone that audit and reconciliation going on, so I'm managing those.
Okay.
Coding and,
Okay.
like, valuation, the company valuation.
Do you think that you can use the neural networks for it?
We are using that artificial intelligence for understanding what document is coming, whatever document we are receiving from the client, and like Microsoft and one mostly Hollywood heroes getting the emails with their accountant, valuation of their properties and assets.
Okay.
So by neural network, we understand what breakdown, all breakdown is happening here.
Okay.
It's coming to the organization, and we are managing what audit and reconciliation we use.
Okay. All right. Fair enough. Okay. All right. Anything else? Anyone else has any internship or work experience? Yes.
So worked in Reliance Digital for about 8 months in a retail sales position,
Okay.
and
as the job was not so good, then pivoted towards cybersecurity with a particular emphasis on online privacy and security.
Okay.
The highlights of that include pursuing an email marketing internship with a Harvard professor, and secondly, I've also worked as a teaching assistant for one of the diploma courses of Red Hat, a subsidiary of IBM. So
Okay.
that pretty much
Okay.
summarizes
All
it.
right. Do you see any use case where you can apply machine learning or AI or anything?
I'll tell you, sir, where the gap is. Like what
Okay.
we've been doing back there was entirely front end and doesn't involve much of the LLMs. We only have the rudimentary understanding of Python and a fairly good understanding of Linux operating system in general, the Arch Linux, etc.
Yeah. I mean, listen, if you think about it, it's not necessarily that you have to say the artificial intelligence is all about LLMs, right? I mean, on the day when I talked about is that what is intelligence? If you don't know something, how it's being done, that's magic, that's intelligence, right? Roughly, that's what it is.
Yeah.
My first encounter of sensor-driven, somebody said it's a sensor, when the doors open themselves, that was like a wow moment. Okay, this can happen. So now it's very common, right? So anything that, also same thing here, if you think about is driverless car, that looks like, is it even possible? Now it's working. Is it working 100%? No. Is it working 99%? Yeah. But is the 1% failure rate acceptable? Right? That's the question. Now, these are some of the things we'll talk next week in terms of what can go wrong. What's the impact? Is it positive, negative? Are the negative impacts worth having, or the other way? Are the benefits worth having so that 1% bad outcome is acceptable or not acceptable? Right? Okay. Anybody who did a project either on AI or ML or anything related?
So I'd like to add on to it, like few months back I pursued a course of prompt engineering. However,
Okay.
the mentor himself was only a end user of mostly front end AI tools like ChatGPT, etc. So what he taught was fairly rudimentary, like the act as prompt which we've discussed in this course, and like in order to oversimplify something, like explain it to a 6th grader, then eventually working up like to a 8th grader, 10th grader. Compared to that, sir, I mean the level of increase which we are having from that course to this course is quite astonishing.
Okay, so, all right. I mean, listen, we could have gone even more detail also, but the prompt engineering is both science and art, if you think about it, right? So, even as an end user, you can do a lot because you have a lot of controls that are available to you. And as a matter of fact, you will see that with a lot of good prompts, these large language models can do a lot of actions, lot of generative capabilities, right? If you do have API access, then obviously you have a lot more world open to you. Because if you think about it, with the API access, you can actually change their knowledge graph, which you can't necessarily, which you can still do using prompt engineering by providing the supervised learning examples, but you can't really control how exactly they're going to use it if you have API learning. And one other thing, it's not here, is RAG, which was a retrieval augmented generation, that you can increase the knowledge base of the LLM. So that's another aspect of what you can do once you have access to the API into the language model. All right, anybody else? How much is the access here? So one thing I've never asked that. What do you guys normally have seen, like ChatGPT or any other model, or what do you have access to? Sorry? Copilot, the GitHub Copilot or Microsoft Copilot. Microsoft Copilot. Is that the only one that you have access to? Or you must be using Bing, then Bing also has a...
Gemini, Llama 3.2.
How are you accessing Gemini or Llama?
So free.
No, okay.
Web browser.
Okay, so you go and then register there and then you have access to it. Okay. What's the best thing somebody can tell me that you've done with, let's say, Gemini, Llama, or ChatGPT? What's the best you have used these things for? Code generation? Mostly? Huh? Generated a data set also. Okay. Code generation, data set. What else?
Whole research report.
Sorry?
Whole research report. Research report with help of hypothetical data.
Okay, so you generated a research report. So did you provide the data, or you said generate the data, generate the report, everything?
So initially I provide some data.
Okay.
For more forecasting, for more data set, I suggested go for hypothetical data.
So you generated the synthetic data and then you ask it to produce some report. Now that report was what? Some charts and graphs and something like that?
Yes.
Did you do it one step at a time, or were you able to write a comprehensive prompt so that it does it automatically in one shot?
Initially I used a comprehensive code, but for customization and changes, I provide a simple step-by-step prompt for the process.
Okay. All right. So there you go. The prompt engineering can actually help you do that as well. Anybody else who has used it for some realistic work?
Image generation.
Image generation. Okay. Good. DALL-E or which one?
DALL-E.
DALL-E. Okay. All right. What else?
Imagen. Sometimes we use Imagen also.
Okay. Somebody else was saying something? Okay, the same kind of thing. Now, just for fun, or were you able to generate something that you think you saved and you think it might be good?
Future children.
Okay, all right. And a lot of images out there which are predicting. Or anyway, all right. Anybody else who wants to share something or anything like that? No? Okay, great. All right, thank you. I'll just, we'll meet next week. All right? Great.